All right, now we're going to talk about KC and KP. These are two different forms of KEQ. The first two different forms you'll see of many through the year of Gen Chem. So they're the only two in this chapter, but this is a sign of things to come with this topic and subsequent chapters. You'll have Ka and Kb and what else? KSP and there's another one or two I'm forgetting. Yeah, just hang in there. So they're all equilibrium constants. It's just different notations to designate what they're for. This is really the biggest difference though. Of all the ones I named, they're more similar than these two to the general idea of KEQ. So these two are the biggest, most different pair. So we're going to talk about them in this chapter. And so KC is what I talked about before. So when I was talking about KEQ in the last video, I was using concentrations. Little subscript C here, concentration. Little subscript P, partial pressures, P for pressure. So gases, you can measure their partial pressures or you can measure their concentrations. They're related to each other, but they're not identical. And so the pressure of a gas, go back all the way to PV equals nRT here, go back to our ideal gas law. That means that P equals nRT over V. N over V, that's molarity, so it's equal to molarity times RT. So this is our relationship between the partial pressure of a gas and its concentration molarity. So that's our molarity, square brackets, that's what we're talking about. So if we look at the formation of water, we react H2 with O2, we get H2O, all in the gas phase, so these will all have partial pressures. This is an equilibrium process, this is reversible. If you took class with me before, you heard me talk about Fukushima. This is what helped blow up Fukushima. They reversed the reactor overheated, it got so hot, it reversed, formed more H2, boom, that react, go back and forth, and eventually you blow the concrete sarcophagus open, and you start spewing radioactive compounds through vented steam. Which is really what happened. I'm not making that up. You can go look it up. But in any event, this is a reversible process. How much it reverses, you got to get that steam really hot for that reverse reaction to start occurring. So temperature does affect equilibrium. We'll talk about that later. But it is reversible. So in a reversible situation, we can write an expression for Kc. We can write an expression for Kp. So Kc, just like we talked about before. Concentration of H2O, our product, squared because there's two of them. Divide by our reactants, so we got concentration of H2, squared because there's a stoichiometric coefficient of 2. 2 are used in the reaction. And O2 to the power of 1, so concentration of O2. Just like we wrote before, no new tricks there. Well, we can do the exact same thing with partial pressure. So partial pressure of H2O squared because there's two of them. Partial pressure of H2 squared because there's two of them, but it's now in the denominator because it's a reactant, and partial pressure of O2. All right, and so all the tricks of calculating from before are true. We just get different tricks with partial pressures. Again, we write the pressures unitless, just make sure all the units match up because Kp is a unitless constant. All right, if you look it up in a table, you don't see any units with your equilibrium constants ever. It is a unitless constant. So, for this example that I wrote over here, we're going to ask a simple question. Are Kc and Kp the same for this reaction at any given temperature? We get it to whatever it is, 700 Kelvin or whatever, 2000 Kelvin, who cares? And we measure our partial pressures, we measure our concentrations, we do these calculations. Would Kp and Kc give us the same number? Well, we can skip right down here and the answer is no if you want, but we'll go through it. So does Kc equal Kp? Well, if I write my expression for Kp, and then I do a little algebraic substitution, I bring this term in for all of my pressures, so that I start getting concentrations plus some extra components. These RTs are going to show up. So my P squared O2 now becomes concentration of H2O, i.e. molarity, times RT all squared. And I do that trick down here with H2, and I do that trick with O2. So H2 is all squared, O2 is not. Well, here's what happens. If all the RTs cancel out, I get the same expression, but they don't. I lose an RT squared here and an RT squared there, but this guy has nothing left to cancel it. And so I get, right here, I get Kc, but Kc times 1 over RT, which is not the same thing. So they are not equal. Now this equality can happen sometimes. It doesn't in this case. And the reason is I have 1, 2, 3 moles of reactants for gases total. There's 3 moles of stuff on the left-hand side in this reaction. But there's only 2 moles of stuff on the right-hand side. And so all of my RTs don't cancel out. But if I had a situation where I had 3 and 3, or 2 and 2, 1 and 1, Kc will equal Kp. But if they are not equally balanced, then it changes. They change from each other. All right, so there's a couple key things here. One, when you're dealing with gases, we'll talk about changing pressure, but it corresponds to this difference as well. This is a very key thing for how pressure, total pressure, affects equilibrium, which is I'll have a whole video on that. And 2, I have snuck in the idea that temperature will also affect equilibrium. So just like it would affect reaction rates, it is a component in equilibrium. And that'll be its own video as well. But if Kc and Kp are going to be the same for a gaseous equilibrium system, that means total moles of products needs to be the total moles of reactants. So that's what I'm saying when I say, like, I've got 3 over here. 3 is not the same as 2. I do not have the same total number. I do not have Kc equals Kp. All right. And you know, when they are equal, then all these RTs, they cancel out and we get Kc. It's as simple as that. All right, so that's the difference between these two. It just depends on what information you're given. All the tricks you do with Kc can be done with Kp. They just find pressures instead of concentrations. And Kc can apply to aqueous systems or, you know, or mixed phase systems as well. Kp is only for gases, only for gas mixtures. So keep that in mind as well. All right, so next we're going to talk about energy landscapes and how that affects equilibrium. So we're going to bring our energy diagrams back into play. One of my favorite, I don't know about favorite, but it's definitely one of the most commonly utilized tools in teaching chemistry. So hopefully it's starting to look familiar now because I know I've used it at least once or twice in this class already. But yeah, so we're not quite done talking about the equilibrium constant, but we got one more video on it.